Hello, my name is Daniel-Michée, and today I'll be presenting on RF antennas and how they connect theory to electromagnetic waves. In this presentation, I'll walk you through how antennas work and how they relate to electromagnetic principles and why they're so important in real world communication systems. So I'll start with an introduction, and I'll say that RF antennas are what makes wireless communication possible. Instead of sending signals through wires, antennas allow electrical signals to be converted into electromagnetic waves that can travel through space. This eliminates the need for physical transmission media and allows communication over long distances. That's why antennas are used in systems like Wi Fi, cellular networks, radar, and satellites. So essentially, anytime we're communicating wirelessly, an antenna is involved. An RF antenna is an electromagnetic transducer, meaning it converts one form of energy into another. During transmission, it converts voltage and current into electromagnetic fields. During reception, it does the opposite. It captures electromagnetic waves and converts them back into electrical signals. These antennas operate over a wide range of frequencies, typically from kilohertz up to gigahertz. Their efficiency depends heavily on how well they're designed and how well they're matched to the transmission line, which affects how much power is actually radiated versus lost. This is where antennas directly connect to electromagnetic theory. A time varying current flowing through a conductor generates an electric field. That changing electric fields then produces a magnetic field. These two fields are perpendicular to each other and propagate together as an electromagnetic wave. This behavior is described by Maxwell's equation, which are the foundation of electromagnetics. So, in an antenna, what's really happening is that electrical energy is being converted into propagating electromagnetic energy that carries power through space. This equation shows the relationship between wave speed, frequency, and wavelength. Since electromagnetic waves travel at the speed of light, the frequency and wavelength are inversely related. So as frequency increases, the wavelength decreases. This is important because the antenna size is directly related to wavelength. For example, a dipole antenna is typically designed to be about half the wavelength of the signal it operates at. This is called resonance, and it allows the antenna to radiate energy more efficiently. The dipole antenna is one of the simplest and most fundamental antenna types. It consists of two conductive elements and is driven by an alternating current. As the current oscillates, charges accelerate back and forth along the conductor. This acceleration of charges is what produces electromagnetic radiation. The current forms a standing wave along the antenna, where it is maximum at the center and zero at the ends. This current distribution plays a key role in determining how the antenna radiates energy. This is a direct application of wave behavior and boundary conditions that we study in electromagnetics. The radiation patterns describe how the antenna distributes power in space. For a dipole antenna, the radiation is strongest in directions perpendicular to the antenna and weakest along its axis. In three dimensions, this creates a donut shaped pattern. Some antennas are omnidirectional, meaning they radiate equally in all directions horizontally, while others are directional and focus energy in a specific direction. Directional antennas increase signal strength but reduce coverage area. So there's always a trade-off between gain and coverage. RF antennas are used in many real-world systems. Cellular base stations use antennas to transmit signals over long distances. Wi Fi routers use them for short range communication inside homes and buildings. Satellite systems use highly directional antennas to communicate over extremely large distances. Even smartphones have multiple embedded antennas to handle different frequency bands and communication standards. Antennas are used in radars and sensing systems for detection and imaging. Antennas are one of the best real world applications of electromagnetic theory. They demonstrate how electric and magnetic fields interact and propagate through space. Everything we learn in electromagnetics, like wave propagation, field behavior, and energy transfer, is directly applied in antenna design. This is especially important for careers in RF engineering, telecommunication, and electronics. In conclusion, RF antennas are convert electrical signals into electromagnetic waves and vice versa. Their operation is based on accelerating charges and the interaction of electric and magnetic fields. Their design depends on frequency, wavelength, and resonance conditions. And most importantly, they are critical components in all modern wireless communication systems. That's it for the presentation. Thank you for your attention, and I'd be happy to answer any questions.